case study in designing an agricultural runoff monitoring system that organizations such as the Western Riverkeeper, our sponsor, could use to detect nitrogen and phosphorus concentrations on farmland. And Riverkeeper here, for example, could use that information in order to identify the good and bad actors with various farms and offer appropriate incentives in order to try to either maintain what the good actors are doing in reducing the amount of pollution that goes into Chesapeake Bay, or encouraging the bad actors to implement more best management practices in order to reduce that pollution. And what we're ultimately going to recommend is using a manned aircraft with a multispectral imagery subsystem for the monitor system, and use that to test a proof of concept with a category-based incentive system framework. And if that proof of concept is successful, to move to a UAV platform for sustained operations. The water pollution isn't just debris getting dumped into the waters. It also comes in the form of excess nutrients. While there is a certain balance of these nutrients necessary for a healthy aquatic ecosystem, too much of it can cause problems, because having too much of those nutrients leads to algal blooms. As that algae dies and decomposes, it consumes oxygen and leads to dead zones, which are uninhabitable for fish and other living organisms. So where does this excess nitrogen and phosphorus come from? Well, the EPA classifies these sources as two types: point source and non-point source pollution. Point source pollution is easier to deal with because it's static in nature. It's clearly identifiable. We're talking pipes, ditches, channels. Non-point sources, on the other hand, are far more difficult to deal with because they're more dynamic in nature. This is when you've got the nutrients in the ground, and as water runs across the ground from rainfall or snowmelt, the nutrients get carried off into nearby bodies of water.
The Chesapeake Bay Foundation did a study to identify the biggest contributors of excess nitrogen and phosphorus in the bay. Based on 2013 data, the biggest contributor in the Maryland region has been agriculture. So what can farmers do? Farmers can adopt BMPs or best management practices. Such BMPs include cover crops, buffer zones, waste management systems, and so forth. But though BMPs are available options for farmers, they may or may not be utilized. So how do we monitor the nitrogen and phosphorus on these farmlands? Well, one system is spectral imagery. Spectral imagery, objects absorb sunlight and reflect energy or unique spectral signatures that spectrometers can capture. There are two types of spectrometers in use today: multi and hyperspectral.
All right, thank you, Will. Good afternoon, everyone. My name is Lisa, and I will begin by discussing the stakeholders. Within the scope of our project, we have three primary stakeholders. This includes our sponsor, the Western Road Riverkeeper, located in the upper left-hand corner of the screen in the green box. We also have the Environmental Protection Agency, or the EPA, as well as the Maryland agricultural farmers that all interact with the upper Chesapeake Bay. Now, one main tension that occurs frequently is a tension between the Maryland agricultural farmers and the Environmental Protection Agency. The Maryland farmers are very resistant to any new laws or regulations enacted by any organizations, including those by the EPA. So in 2010, the Environmental Protection Agency established water quality goals known as the total maximum daily loads, or TMDLs. What we find is that they want to reduce the excess nutrients in the Chesapeake Bay by the year 2025. They've calculated what the baseline should be, and you can see that in both of these graphs indicated by a red line. Both for the nitrogen, located on the top graph, and the phosphorus on the bottom graph, we find that the trend line, although decreasing, is not going to meet those goals. That leaves us with an excess nitrogen amount of around 7 million pounds as of 2013, and for phosphorus, around 1 million pounds that needs to be further reduced. So although the EPA has gone ahead and established these TMDL goals, and they are currently addressing these point source issues, such as the pipes, channels, and concentrated animal feeding operations, as indicated by Harry, there is still a need to address non-point source pollution, such as the agricultural runoff. This leads us into our need, and what we need are systems to be introduced that will help meet this gap. And what we have is need for an incentive system that will actually positively encourage farmers to incorporate more BMPs that will help limit or reduce the amount of agricultural runoff entering the bay. Additionally, we will need a monitoring system that will measure the progress of these efforts. If you cannot measure it, you cannot improve the system. So with our needs in mind, we derived 4 functional requirements. The first one is geared towards the incentive system. For the incentive system, it shall be able to positively encourage these farmers to incorporate the BMPs. Our functional requirements 2, 3, and 4 are all focused on the monitoring system. The monitoring system shall be able to detect both nitrogen and phosphorus levels in the soil, as well as be non-intrusive to the farmers and remote. With those in mind, we went ahead and established a concept of operations. With that, we focused on a monitoring system. The monitoring system will be able to detect both nitrogen and phosphorus levels of the soil. That information will then be utilized by our sponsor, the Riverkeeper, who will collect that data and use it with the incentive system in mind to go ahead and form categories for each farm. That information will then be passed on to the farmers, and the farmers will use it to either maintain their good standings or go ahead and incorporate further BMPs, and the cycle will then continue.
So looking at the alternatives for our monitoring system, we need to house some type of spectral imagery subsystem into a vehicle platform. And here we look at 4 high-level types. Ground vehicles such as ATVs and UTVs, unmanned air vehicles or UAVs, both rotorcraft and fixed wing, manned aircraft, and also satellite. A major cost difference is between the multi and the hyperspectral imagery systems, because a multispectral system can cost anywhere from $3,000 to $6,000, but when it comes to hyperspectral, we're looking at $30,000 and up, and that's just for the imagery subsystem.
All right, thank you, Harry. I'm going to discuss the incentive system alternatives next. We have 5 main alternatives for the incentive system. The first one actually is a report on the nitrogen and phosphorus levels of the farms. It generally will also include a list of what category the farmer is classified under for the incentives. Additionally, there is an awareness report. Now what the awareness report is it's a list of the current state and federal programs that the farmers may or may not be aware of that could offer monetary values for them. Our third option for an alternative is what we are calling the TMDL Gold Card. Now what this is it's an incentive system based on a relationship with the local businesses in the community to help offer discount rates at the businesses for complying farmers. We also have an farmers insurance legislation change. What this alternative is really an extension on the current farmers insurance already available. It is meant to include risk due to profit of loss with implementing new BMPs. Finally, we have an assistance program. This assistance program is geared towards, offering new technology to both cropland and livestock farms. The first is the variable rate application technology. That is for the cropland farmers. What it is it's equipment that can be attached to tractors, and as it passes over the soil, the sensors can read the nutrient context in the soil, and then send that data to the system that will release concentrated amounts of nutrients as needed across the farmland. The benefit to this technology is that it has been found to dramatically reduce the fertilizer costs on these farms. Additionally is the manure digester systems. These are for the livestock farmlands. Livestock produces a lot of manure, and that manure often leads to a lot of excess nutrient runoff into the groundwater system. So what you can do is install a manure digester that will separate the manure into 2 components, both solid and liquid. The solid component can be used as an alternative form of animal bedding, while the liquid is converted into a natural gas equivalent. The benefit of this is that it provides a renewable energy source to the farmers. The cost of this system is expensive and starts at around $250,000 $500,000. However, Cornell University has noted that there is an average payback period of about 5 years.
So going about comparing multi and the hyperspectral imagery systems to see if is the cheaper multispectral system sufficient for the purpose of the Riverkeeper. Well, actually, this algorithm was developed by our rock star colleague Don Brody, who based this off of Beer's law, which states that there is a proportional relationship between absorption and concentration. And with that, we see it's a linear relationship which has an additive property. Now, for the inputs for the simulation, we're inputting the various device parameters for the imagery system, which would be the spectral resolution, the range, and its device error. Also, and we test these against a distribution of chemical elements, which we based off of typical elements found in plant growth and with the concentrations and parts per million. And we gathered data in terms of the spectral signatures for each of those elements from the National Institute of Standards and Technology. Now, for the outputs, we wanted to be able to compare what is the determined concentration for nitrogen and phosphorus compared to the actual that we know is in it, because, well, that's something that we set. So just to show what's actually going on in this model, let's look at a simplified example. Let's just say that this is the spectral signature for 1 part per million nitrogen. Now, based on the additive property, if we have 2 parts per million of that, the intensities would stack up at each wavelength. Now, if we look at it with a multispectral system based on the bandwidth it's able to see, it might not be able to see finely enough for, say, these 2 spectral lines here, and so it'll just combine those intensities because of its bandwidth limitations. And then we incorporate the error by in terms of a normal distribution based on where the device error is, and based on where the actual intensity is. Excuse me, fumbling there. So let's just say we have a whole jumble of spectral signatures, and we want to identify what is the concentration for nitrogen. Well, what the simulations does is it goes wavelength by wavelength. So here, for example, we'll look at the first wavelength, and based on what we know about nitrogen's signature, we see that there could possibly be 3 parts per million nitrogen. Then it moves on to the next wavelength and sees, well, there could really only be 2 based on what I know about its signature, so therefore at the previous wavelength there must have been noise from other elements. Going to the next one, the simulation knows that there's no intensity really here at this wavelength for nitrogen, so thus this is probably noise. And it continues this process through each of the wavelengths to ultimately identify, in this example, that there's 2 parts per million nitrogen.
To evaluate the different vehicle platforms, we took these equations that represent ACR from an MIT study. From there, we were able to, by assuming that the imagery system is the same in all vehicle platforms for comparison purposes, we were able to garner a unitless coefficient for the imagery aspect of the ACR equations. To derive the ACR equation for each of the vehicle platforms, we took the coefficient and times it by the vehicle velocity and height above ground. We differentiated between fixed wing and a rotorcraft because they have different velocities, but we evaluated both at 400 feet due to FAA federal regulations. Also, we evaluated the manned area of vehicles at 2 different levels. One is at 500 due to FAA regulations, and the other is at 3,000 due to limitations with the multispectral system. And while running our experiment, we set our device error between 1 and 9% to be able to take a look at the average nitrogen and phosphorus detection error rates between the multispectral and hyperspectral system. This will give us an opportunity to compare and see the differences between the multispectral and hyperspectral systems. With the vehicle platform, we were able to get the ground resolutions from the manufacturers. We designed a scorecard for our incentive alternatives. In ranking our incentives, we did a DEFI method where we use scalability, implementation, maintainability/sustainability, and community value.
Thank you, Will. My name is Hoon Chung, and I will go over the results of simulation and analysis. This is simulation results. The top chart shows the data input for simulation, and it also shows the average and nitrogen phosphorus detected error for multi and hyper imager systems. at different points of device error. The bottom graph shows its graphical representation. As you can see, the trend line increases as we increase the device error. And notice that up to 3% device error, the difference between the multi and hyperspectral detective error is not significant. In fact, the actual difference between those two is less than 1%. And you have to notice that 2% device error is the maximum device error stated directly from the manufacturer. As systems engineer, we want to be pessimistic, and we run our simulation up to 9%, and it still shows relatively small amount of difference between the hyper and multi. So considering the high cost of hyperspectral imaging system, use of multispectral imaging system for this project is acceptable. This is our value hierarchy came up with our sponsor. The major goal of this project is, of course, to reduce the nitrogen and phosphorus in agricultural runoff. In order to do so, we have to have some kind of monitoring device, which is called the monitoring system, and we want to have incentive system that encourage our farmers to utilize the best management practice. In our monitoring system, we value the efficiency of the measuring device and area coverage rate. And we also see whether the systems require specialized operator, such as licensed pilot for Cessna 152. On the other hand, for incentive system, we value the easiness of systems implementation and sustainability. And we also see the scalability, meaning how easy it is to expand our system to other locations. And lastly, we also see the community factor, whether it is community friendly or not. So having the values and preference from the sponsors, we came up with this monitoring systems ranking. The top chart shows our rankings for alternatives. The highest ranked system was manned aerial vehicle at maximum height, which has reasonable ground resolution and has the second highest ACR, area coverage rate. Followed by fixed wing unmanned aerial vehicle has the second highest rank, which has better ground resolution than manned aerial vehicle and does not require specialized operator. And thirdly, we have the rotor UAV, which has almost same attributes as fixed wing UAVs, but it has slightly less average coverage rate due to its speed. So the question is, how much does each system cost? For example, for a manned aerial vehicle, it costs nearly $40,000, including multi-spectral imaging system. Whereas for both fixed wing and rotorcraft UAVs, it costs less than $25,000, including the same multi-spectral imaging system that we're having for manned aerial vehicle system. In case of change in sponsors' values and preference, we have done some sensitivity analysis. The top chart shows the effect of change in weight of ACR to the rankings. We're currently standing around 24% of ACR, but if you increase that amount up to around 65%, the ranking changes. The system that has the best ACR becomes the highest rank, which in that case is satellite. Similarly, the ground resolution. If you increase the weight of ground resolution up to around 95%, then the system with the best ground resolution becomes the highest rank, which in that case is ground system. For incentive systems, due to nonlinear relationship between the alternatives, we have to normalize the Likert scores and calculate the t-scores. With calculated t-scores and given weights of scalability, implementation, sustainability, and community, we calculated total weighted score. As a result, the TMJ Gold membership card was the highest rank in the system. And farmers insurance and assistance program legislative change were tied up as the second highest rank. And thirdly, we have the nitrogen and phosphorus report. Notice that the difference between each alternative is not that significant. So if you change slightly, if you change the Likert score slightly, then it might change the rankings.
So while the ground vehicle actually ranked pretty high in terms of our cost-benefit analysis, it violates one of our requirements in that it is intrusive to the farmers, because to utilize a ground system, you would have to drive on the farmland. Now, the UAVs have the best balance between cost and benefit, but they are currently illegal for commercial use, that is. So when we were evaluating the system, we did the 400 feet. The FAA regulation was based off of for hobbyists to fly UAVs, but in terms of commercial use, those laws are not in place. However, the FAA has recently published an NPRM, or Notice of Proposed Rulemaking. This is in February of this year, as a major step in towards establishing those laws. And some of the highlights from this include that UAVs could fly at a max altitude of 500 feet above ground level. And they do know that they want the operators to pass a written test, which still is not as extensive a process as becoming a licensed pilot, and that the UAVs must weigh less than 55 pounds. Now, the UAV system that we used in this analysis, with the multispectral imagery system, would weigh under 7.5 pounds. And also noting the NPRM, they look at 4 major markets in terms of potential markets, one of which is agriculture. So, and using the ranked incentive alternatives, we put that into a framework based on category green, yellow, red, where the green category will be your good actors, or red will be your bad actors. And because we want to positively encourage these farmers, even if they are a bad actor, we're not trying to punish them necessarily, but still offer certain incentives to try to help boost them in the right direction, whereas the good actors have access to more incentive options. And so what we're recommending is to utilize a manned aircraft with a multispectral image system, as it had the highest value, but also the highest cost, and use that to test the proof of concept. Now, if that proof of concept is successful, we recommend moving to a UAV platform, as those laws are being established by the FAA. And with that, I'd like to thank you for your time, and are there any questions or comments for us?